Welcome, my dear students and friends, to a session on Unijunction Transistor Working Principles through Learning Management System and e-learning program conducted by Department of Collegiate and Technical Education. Myself, Omna MH, lecturer from Government Polytechnic, Belagavi. Today in my presentation, I am going to brief you about UJT construction, equivalent circuit diagram, and its VI characteristics. Then we will see how UJT operates as a relaxation oscillator. We will try to solve some questions. Then we will study the working of synchronized UJT pulse triggering circuit with respect to its circuit diagram and waveforms. Later on, we will compare different firing circuits, that is R firing, RC firing and UJT firing methods. And lastly, we will have some questionnaires on synchronized UJT pulse triggering circuit. Before explaining working principle of UJT as relaxation oscillator, we will briefly study the construction, internal circuit of UJT, its symbol, and the VI characteristics of unijunction transistor. So UJT is made up of N-type material or a silicon base in which P-type emitter is embedded. It has three terminals, emitter, B2 and B1, that is emitter, base 1 and base 2. So between these two bases, there is an unijunction which behaves like an ordinary resistances RB1 and RB2. These are the internal resistances, where RB1 is the internal resistance from B1 to E and RB2 is the internal resistance from B2 to E. And this is the UJT symbol. Now, if we apply a emitter voltage between E and B1 such that this is positive and this is negative. Now, slowly increase this emitter voltage from 0 until this VE is less than eta into VBB. So VBB is the supply voltage between B2 and B1 and eta is the intrinsic standoff ratio which you have discussed while in your first unit about the UJT. Now, if the voltage between V1, that is B1 and B2, where VBB is the voltage between V1 and V2, the PN junction is reversed biased and emitter current will flow in the negative region. So this is shown in this curve. This is the negative region where the current is negative for a small amount of time. Now, if you go on increasing the emitter voltage such that VE is equal to eta into VBB plus VD, IE becomes positive. So IE is the emitter current which becomes positive and this is the direction of the IE which will be flowing, and the junction between E and B1 will break down and it starts to conduct. So this is the point where the emitter current goes into positive state, and VD is nothing but the forward voltage drop between E and B1. This point A is called as the peak point. The corresponding voltage is the peak voltage and the corresponding current is the peak current. At this point, what will happen is emitter will start injecting holes into this lower base region B1. Because of the increased number of carriers, the base resistance RB1 will decrease. So due to this, emitter voltage will reduce and emitter current will increase. Hence, this is called as the negative resistance region. So this is the region where the emitter voltage is decreasing and current is increasing from point A to B. So this is the negative resistance region. So after a certain point B, the B1 region gets saturated by the charge carriers emitted by the emitter. So now once it is saturated, the resistance RB1 will further not decrease anymore. So this will make the current to increase, and increase in the current will drastically increase the voltage. So this minimum point where the transition of this current and voltage takes place is called as the valley point. The point B is called as the valley point. So the negative resistance region is the region between these two points A and point B. That is peak point and the valley point. So this, your UJT or unit junction transistor is going to be operated in the switching characteristics region is in this negative resistance region, that is between A and B. Now UJT is going to be used to turn on the SCR. Now coming to working of UJT as relaxation oscillator. Due to this negative resistance region, UJT can be operated as an oscillator. So this is the circuit diagram of relaxed oscillator where R1 and R2 are the external resistances connected between B1 and B2 terminals of UJT. The value of R1 and R2 should be such that it is lesser than the internal resistances RB1 and RB2 of UJT. The charging resistance R value should be such that its load line will intersect the load characteristics of the device in the negative resistance region only. So this is the negative resistance region. So the load line of this resistor R also should intersect in this region only. Then only this UJT will be operating as an oscillator. Now when a source voltage VBB is applied across capacitor, C tried to charge through this R exponentially towards VBB. During this charging, emitter circuit of UJT is in open circuit. Now capacitor voltage will be equal to the emitter voltage as shown here. That is VC is equal to VE, which is equal to VBB into 1 minus e to the power of minus T by RC, where e to the power is nothing but it is charging exponential. So this is the exponential charging of your capacitor, where tau 1 is nothing but the charging time constant of the capacitor and its value depends upon this R and C value. When the emitter voltage VE, here it is VC, that is the emitter voltage VE or VC reaches the peak point voltage, this is the peak point voltage, then VP is equal to so I have already told you eta into VBB plus VD. So what will happen is the junction between E and B1 will break down. As a result, UJT turns on and capacitor C rapidly discharges through this low resistance R1. So this is the low resistance R1. So through this, the capacitor which is charged through this resistor R is going to discharge. So this is the discharging path of the capacitor. Now the discharging time constant. So this is the discharging waveform which we can observe. So the discharging time constant is depending upon R1 and C. So that is tau 2 is equal to R1 into C. So here the tau 2 or the discharging time is always lesser than the charging time. That is the time taken for a capacitor to charge from its initial voltage VV to its peak voltage VP will be always more compared to discharging of the capacitor from peak voltage to valley voltage. So once the emitter voltage decays to this valley point voltage, UJT is turned off. Here, one thing we have to keep in mind that capacitor voltage will always charge between valley point voltage and peak point voltage. So this valley point voltage is the initial voltage of the capacitor. Hence, the time required for charging through this large resistance R is given by Vp is equal to eta into VBB plus VD, where VD is the forward voltage drop of the emitter B1 junction. Now if you assume VD as equal to VB or the valley voltage and eta is the intrinsic standoff ratio. So now eta can be obtained through this exponentially charging capacitor through the RC. Now you substitute the value of VD and eta in this equation. Now the equation will be Vp is equal to Vv plus VBB into 1 minus e to the power of minus T by RC. So this is the equation we will get if we substitute these values. Now if we remove T value from this equation and apply logarithmic to the base E, we will get the equation as T is equal to 1 by F RC, that is R into C ln of 1 divided by 1 minus eta, where T is taken as the time period between the charging and discharging of the capacitors. So this is the time period T from charging, that is the capacitor charging point from valley point to peak point. So once the capacitor had been charged to the peak point, it is going to discharge a pulse, that is through the resistance the capacitor is going to be discharged. So the current is flowing in the resistor and that will give you a output pulse. So this is the output pulse which is being obtained at this region, discharging region of the capacitor. So this time period of charging of the capacitor can be considered as alpha. So the firing angle is nothing but omega into T is equal to omega into RC ln of 1 divided by 1 minus eta. Now let us consider some of the questions from the slides what I have previously discussed. So the question says, for a constant value of capacitor C, if R value is increased, the number of UJT pulses obtained in each half cycle is, the options are, it decreases, it increases, it has no effect. So try to read the question again. The constant value of capacitor, if R value is increased. So try to remember the circuit diagram and the waveforms which I had drawn previously. So there, if you remember, you will be able to get the answer to this. The answer is, the pulses obtained will be decreased because R value is the one through which the capacitor is going to charge. If the capacitor charging time is less, then automatically the pulses obtained will also be reduced. That is the charging time. Time required for capacitor to charge from value voltage to peak voltage also will take more time. So in that region, that is, so if the R value is increased, then the capacitor with a constant value, the UJT pulses obtained will also be decreased. So it is not going to increase or no effect will be not there. There will be an effect, that is, it is going to decrease. The next question is, what is the value of charging resistor R for a firing frequency of 2 kHz with a capacitor of 0.04 microfarad with the eta value of 0.72. So the options are 12.3 kilo ohm, 9.82 ohms, 15.2 kilo ohms, 9.82 kilo ohms. So for this you have to apply the formula which I have been derived in the previous slide. The time requirement for the capacitor, for the charging time requirement of the capacitor, T value. So the answer is 9.82 kilo ohms. So here you have to apply T is equal to 1 by F RC ln of 1 divided by 1 minus eta. So if you substitute the eta value, the capacitor value and the frequency is being given, so the time is nothing but 1 by frequency, then you can able to find out the R value. So the R value will be 9.82 kilo ohms. The next question is, the UJT may be used as an amplifier, a sawtooth generator, or rectifier, or none of the above. Here for this question you have to remember the waveform of the UJT, the pulses generated by the UJT. If you try to remember it, then you will be automatically getting the answer to this. The answer is sawtooth generator. So a sawtooth generator type waveforms will be obtained. So UJT is not being used as an amplifier or a rectifier, but we can use it as a sawtooth generator depending upon the waveforms which has been obtained by the UJT pulses. This is the circuit diagram of synchronized UJT pulse triggering circuit. So the circuit consists of 4 diodes, resistor, capacitor, Zener diode, and a current limiting resistor R, the pulse transformer. So the diodes D1 to D4 are used for rectification purpose. So these diodes D1 to D4 are used as a rectifier which will convert AC to DC. So the output value of VDC is being obtained. Vs is converted into VDC. Then R1 is the current limiting resistor which reduces the diode rectified output voltage VDC to a suitable value for this Zener diode and UJT. So the Zener diode, what it will do is, it will clip the rectified voltage to a standard level of Vz. So this is the Vz is the standard level of voltage. So this is a constant voltage and this voltage is being applied to this RC charging circuit as an input to this UJT. Current I1 is the charging current which will be flowing through the R and C. So your capacitor is going to charge through this charging current. So the voltage across the capacitor is marked as Vc. So Vc is the voltage across the capacitor. So the charging current is being depending upon the R value. When capacitor voltage reaches the unijunction threshold voltage of this UJT, that is eta into Vz. So eta into Vz. So Vz is used as it is serving the purpose of VPP supply voltage. So the Vz is similar to the VPP because Vz is the input to this UJT. So the emitter P1 junction of UJT breaks down and UJT is turned on. Now the capacitor discharges through this pulse transformer, sending a current of I2. So this is your I2 current. I2 current will be flowing through this pulse transformer and capacitor. As the current I2 is in the form of pulses, windings of the pulse transformer have pulse voltages at the secondary terminals. These pulse voltages will be applied for gate and cathode of the SCR to trigger the SCR. Since the number of secondary windings of the pulse transformer is more than 1, so the two SCRs it can be able to turn on. So this type of triggering method we can able to control the alpha from 0 to 180 degree. That is by varying the resistor R. So by varying this resistor R, alpha can be controlled up to 180 degree. Since Vz is 0 at the end of each half cycle, the synchronization of the triggering circuit with the supply voltage across SCRs is achieved. Hence the name synchronized UJT pulse triggering circuit. So these are some of the waveforms of synchronized UJT pulse triggering circuit. So this is the input voltage which is sinusoidal in nature, and this is the rectified output voltage which is going to convert AC supply voltage into pulsating DC, and it is varying from 0 to pi as that of the supplied voltage. So this is the output voltage across the Zener voltage. Here we can able to observe that the rectified output voltage has been clipped to Zener voltage by the Zener diode. So the next is the capacitor voltage waveforms. Once the capacitor is been charged from its valley point to the peak point, so this charging period is determined by alpha. So here a pulse voltage is being released to the pulse transformer whenever the capacitor voltage reaches the peak point voltage, that is nothing but eta into Vz. So this is the pulse voltage obtained. So whenever there is an output voltage or the pulse voltage, then the output voltage is obtained. So this is the conducting period of the SCR from alpha to pi. This is the off period of the SCR from 0 to alpha. So now let us have comparison between R triggering, RC triggering and UJT triggering circuits. So first is the range of firing angle. So if you see in the R triggering circuit, the firing angle will be from 0 to 90 degree only. So that in case of RC triggering, it is 0 to 180 degree. So UJT triggering is also 0 to 180 degree. If you come with the power dissipation of the circuit, in R triggering, the power dissipation is high, and in RC triggering also power dissipation is high, because there is a continuous pulse of voltage. That is not pulse also, it will be continuous voltage will be applied across the gate. So the continuous power dissipation will be taking place in case of R triggering and RC triggering. But since in the UJT triggering it is a pulse type of triggering method, so only for a short duration of time the UJT pulses are used, so the power dissipation will be low. So if you come to isolation part, there is no isolation provided in case of R triggering or RC triggering, but we have an isolation of pulse transformer in case of UJT triggering. So firing of multiple SCRs, here we can't fire multiple SCRs even in case of RC triggering also. But there is a provision due to this pulse transformer with many secondary windings, we can able to use or turn on many SCRs at same time. Coming to the cost of the circuit, R triggering circuit and RC triggering circuit cost is very less compared to UJT triggering, where the cost is slightly more than the R and RC triggering circuit. The last one is the types of triggering. So R and RC triggering are AC gate type of triggering, but UJT triggering is a pulsed triggering method. Now let us recall what all we have studied through these multiple choice questions. So the question says, in synchronized UJT triggering of an SCR voltage, VC across the capacitor reaches UJT threshold voltage thrice in each half cycle, so that there are 3 firing pulses during each half cycle. The firing angle of the SCR can be controlled. Answer is thrice in each half cycle, once in each half cycle, twice in each half cycle, or none of the above. So what is the answer? Capacitor is reaching to its peak point voltage 3 times in each half cycle. So there are 3 firing pulses obtained in each half cycle. Okay, because in each half cycle the SCR is be obtained So now let us see the answer. It is once in each half cycle. So how it is once in each half cycle? Because once the SCR, even though it is being charged and discharged in this full half cycle, 3 times if it is reaching 3 times peak value and discharging, but also a single pulse. So you will be able to get 3 pulses. 3 times it is discharging. So 3 pulses you will be able to get. Even though 3 pulses you will get in each half cycle, the firing angle of the SCR can be controlled only once, because only one pulse is enough for SCR to turn on. There is no requirement of the second or this third type of pulses. Once SCR is turned on, again even if you remove the gate also, the SCR will be in the on state only. So only one pulse is enough, or one firing angle of the SCR can be able to control in each half cycle. Next, the improved version of the UJT oscillator triggering circuit is, the options are ramp and pedestal triggering, RC triggering, cosine pulse triggering, and the last is ramp triggering. So what is the answer for this? UJT oscillator triggering type of method only you have to choose. The answer is ramp and pedestal triggering, because ramp and pedestal triggering is the improved version of UJT oscillator triggering. RC triggering also UJT will not come into picture. In cosine pulse also it is a comparators type of circuits. Ramp triggering, only with the ramp triggering you will not be able to get the oscillator part. So both the ramp and pedestal triggering is required, as so it is an improved version of the UJT oscillator circuits. So in ramp and pedestal triggering, we can able to turn on 2 SCRs at the same time, which are connected back to back, and hence we can able to get the AC type of controlling operation. Next, the question is, which of the following pairs are correctly matched? So here there are 3 parameters being given, and this is the UJT triggering methods. So for the first one, firing of multiple SCRs. So in UJT triggering it is possible, yes, and isolation possible, range of firing angle 0 to 90 degree. So what is the answer for this? The answer is both 1 and 2 is correct answer, because we can able to fire the multiple SCRs also, and isolation is also possible due to the pulse transformer, but the range of firing angle is more than 90 degree, that is we can able to control the SCR from 0 to 180 degrees. So both 1 and 2 is correct, and the third one is wrong. Thank you.